Hello, hear me? Yes? Okay, great. Welcome to week 13, lecture A. Today we are going to do our final lecture on digital controls. And first of all, let's take a look of our quiz. So you can see the quiz. So we have the first question is you have sinusoid, sine omega t. Omega is a 2 pi fs. Fs is the sampling frequency is 10 hertz. And then you sample at 9 hertz. What are the first 5 frequencies in the sampled signal? So we are working on that one with you. And later on, all these questions is easy to answer. And there's also a very simple discretization, including ZOH. So how to do that? Basically here, you need to apply what they call PFE, partial fraction expansion. Then you look up the table, you'll be able to get the G of Z, okay? So we are going to study how to do the sampling theorem. So let's do a very quick review. Before I do that, let me put my chat box in here and put my video in here. Okay, so we have seen that the signal, if we do not sample properly, so you thought this is a straight line, but it could be like this, right? So then we talked about sampling is nothing but going through a continuous time signal times the pulse train like that. So you have to sample the data. So went through this sticky property of impulse, delta of t. It's a shifting property, okay? So we talked about sampled data as f star, how we can start the Laplace transform of it. In the end, we end up with this, okay? So it turns out that there's a duplication of the spectrum in here, okay? So visually, so we have a signal that is a band limited signal, or so any frequency above B is 0. So all the energy of the signal in this narrow band. So this is called band limited signal. So in real world, your signal usually is band limited, okay? So after sample, then basically you are duplicating your original continuous time signal spectrum to different places until infinity. The center frequency is multiples of your sampling frequency. So we stopped it here last time. We were talking about sampling frequency. Okay, sampling frequency means if your sampling frequency is not large enough, then you have some overlapping area in here. Okay, so then you will not be able to undistort. Okay, so the signal is no longer, it will become aliased. Okay, become aliased. It cannot go back. Okay, this is also called signal reconstruction from the sampled data. So from continuous to discrete, okay. But from discrete, you cannot imagine what is the continuous. It's just like in here, okay? In here, you cannot say what is a straight line or this one, okay? If your sampling time is not fast enough, okay? So the sampling frequency is if you have a sinusoid, okay? If you have sinusoid, after you have sampled all this type of thing. So these are all frequency on the time domain signals. What about frequency? Frequency domain is you have this single line. This is 100 hertz. Okay, 100 hertz. If you sample at 200 hertz, that's fine. Okay, that's fine. So your next one is here. Okay, center frequency is here. Okay, so your sampling frequency is 200 hertz. Okay, so you move this whole thing to center that instead of centered at here. Instead of centered at 0, you centered at 200. So 200. So then this line becomes this line. Okay, And next to the center is 400 hertz, okay, 400 hertz. Then your center, the frequency is here. So it becomes 100, 300, 500. So all these are the components contained in this signal. So you have 100 hertz, you have 300 hertz, I have 500 hertz components in there, and infinitely many, okay? Because this will be duplicate forever, just like we have seen in here, duplicates, okay? Duplicates, okay? So this is good. We can see if we do a low pass filter, we can filter out all the higher frequencies. It's fine. But if we sample not fast enough, this is less than 2B. So in here, our B is 100 hertz, right? The band limited. So this is 100 hertz. So if you sample slower, then you will have aliased frequencies 50 hertz. So how you can identify this 50 hertz? Okay, so this 50 hertz is less than 100. If you do low pass filter, you filter out the high frequency, but you still have this 50 still very still there. Okay, you cannot kill this one. You cannot kill this 50 without hurting the 100, right? So you cannot do that. It's very difficult. So sampling frequency is very important. Here is the sampling theorem. It's also called Shannon sampling theorem. So your sampling frequency should be higher than the B, 2 times of the B. Okay, 2 times of the B. So that is FS 2B, minimum is 2B. That 2B is also has a name. It's called Nyquist frequency. Okay, Nyquist frequency. So you can get rid of all those duplicated high frequencies by using low pass filter. So, so this low pass filter, okay, anything beyond this can be canceled out. So this is called low pass filter. So we put this anti-alias filter in here. So this is low pass filter. So before you sample, you put a low pass filter in here. So then it's called anti-aliasing. Okay, anti-aliasing. So let's do our first question here. So you have sinusoid that is 10 hertz. I am sampling at 9 hertz. Okay, sampling at 9 hertz. So in my frequency domain, okay, so this is the frequency domain. So this is my 0 hertz, okay, 0 hertz. Then the original signal is my 10 hertz, okay, 10 hertz. But remember, I'm sampling at FS is 9 hertz. So to do that, I'm going to do, look carefully. I'm going to do 9 hertz here, 18 hertz. So this is 9, this is 18. This is 27. This is 36. Okay. So all these points corresponding to the duplicates of this center frequency. So this is 0, this is 9 hertz, this is 18, this is 27. You see what I mean? The multiples of 9 hertz is your sampling frequency. So I'm using this dot in here. So I'm going to do the first shift. So first of all, before I sample, I have sinusoid. So this is my bar of single term sine omega t. Okay, while omega is 2 pi times fs. My fs is 9 hertz. Okay, 9 hertz. So this is a continuous time signal. I'm going to sample it. So when I sample it, then my spectrum will get duplicated of this original black one infinitely. Okay, so basically you also have something called here. So we say this is 0 and 0 prime. Okay, have a good habit. This is minus 10 hertz. Okay, so now what I'm going to do is lift this 0, 0 prime and 0, 0 prime and 0. I lift it and shift. Originally this is centered at 0, right? So now I'm going to center that 1 times fs, which is 9. Okay, which is 9. So I'll shift this from 0 to 1f. Okay, so this is 0 is 0 times fs. Shift this one, I'm going to get what? Shift this 0 to 9. Then this 0 will shift to what? Shift to 9, all right? So I shift to here. This is 9. So this is 19. So I call this is a 1. Okay. So this is 19. 19. Okay. This is 19. And also I have this one. This is a minus. Go to 9. So this is a 9. Okay. I move 10 hertz. So and center that here. So I'm going to have a minus 1 in here. Okay. So this will be my this will be my 1 prime. Okay. 1 prime. But we can ignore the left-hand side. But when we shift, we need to consider the left-hand side, the negative 1. So, okay, so this is a 1 duplicate. So basically, I'm moving this guy to here, right? So we only have this one, right? So then I have another one here. Okay, so it's clear. So I'm going to again, I'm shift to 2. I'm doing a 2 fs, which is 18. Okay, which is 18 is here, right? It's 18. And then I put it here, plus 10 is 28. Okay, 28. So then I know that this 28 is my 2. But if I move 10, then I got what? So I have 19. I move this side is 9. So I have 9 here. So this is my 2 prime. Okay, 2 prime. Make sense? Yeah. So this 2 prime is actually our what is called the frequency of aliased frequency. Aliased. So this is aliased. So let's continue to do this game. So change another color. Change it to this color. So I have 3 fs. What is my 3 fs? 3 of fs is giving me 27. Okay, so my 27 is here. Add 10 is 37. So I have 37 in here. So then this is my 3. Where is the 3 prime? 3 prime is you minus 10 is 17. 28 minus 10 is 18. So you got 18 in here. So this is a 3 prime. So, okay. Okay. So you can see that what is the, so you can keep doing the 4fs. 4fs is here. The center point is here. Okay. The center point is here, 36. Then you add 10, you got 46. Okay. Because your original signal is 10. So you have 4. Okay. What is the 4 prime? 4 prime is you have 36 minus 10 is 26. Okay. So it's 26. Okay. So this is 4 prime. Wait. Yes. Yeah, it's 26. So this is a 4 prime. Okay, 4 prime. So now what I'm going to summarize is I have 10 hertz. I have 9 hertz, 10 hertz. Then I also have 18 hertz. Okay. Then I have also 19 hertz. Okay. Then I have 26 hertz. Then I have 28 hertz. So if I want to write the top 5, we just do this, okay? So those are the frequency components due to the sampling for the top 5. Okay. All right. So you should be able to do that. Okay. So maybe you feel like, this is kind of tricky. So let's do this. Fs is 10 Hertz. Okay. So, but sorry, my signal is signal omega is 2 pi times 10 Hertz. Okay. But my sampling frequency is 15 Hertz. Okay. So this is the example we're seeing in here. This one. Okay. I'm going to show you how this 50 is coming out. Okay. So let me do the same thing here. So I have the frequency in here. So my original is 0 Hertz. So 0 times Fs. Okay. So then this is my 10 Hertz. Okay. Actually, in our system, we use the 100 and I use the 150. Okay. But according to the sampling theorem, you have to sample 200 Hertz or higher. But now I didn't sample that fast. I sampled slow. So we'll see what's going on. So this is 100 Hertz. Okay, 100 Hertz. So I have a bar in here. So this is my continuous. The black one is my continuous time. So what I'm going to do first is to identify my, what is 1 times Fs? So this is here, 150. So this is 1 times Fs. Then another one is 300. Okay, this is 2 times Fs. Okay, 2 times that. Oh, come on. I need to remove this. So you can do 400. You have to do a 400. Next one is 3 times Fs, right? Fs is 150. So what I'm going to do, the first component is blue. So I shift everything. So this is my 0. This is 0 prime. I lift 0 prime 0, center at 0 Fs, lift and shift and center at 150. Okay, so then basically you have 250 here. Okay, the 250 here. So this is 1. So also this is a minus 100. So you put 50. So there you have 50. So this is 1 prime. Okay, but you can keep doing the game. Lift this one and center at 300. Then what you are going to get is 400 here. So the 400 is this one. Okay, so this are 2. This is a 2. But minus 100 is 200. So it's around here. So this is 150. It's 200. So this is 2 prime. Okay, 2 prime. So you can keep doing this one and center at this one. So you are going to have 550. Okay, so you have 550. Let me continue this. 550 is this one. So this is 3. Then you minus 100. So it's 350. Okay, it's this one. So this is 3 prime. Okay, so you can see the whole system. The first 5 is 50 Hertz. No. So sorry. This is a 50 Hertz. This is the first. Second one is 100 Hertz. The other one is 200 and 250. Okay, so then you do 350 and you do 400 and you can do more. Keep writing. So you see what I mean? So this is the way. But in our example here, we only showed you the first 2. We only showed you the first 2. Okay, but there are infinitely many of such kind of thing. Okay, if you add a low pass filter, you can cancel out all the higher frequencies, but you still have this 100 left. You keep 100, you'll keep 50. So that the aliasing is very bad. If you have an alias, the signal is very bad. will make your life much miserable. Okay, so anti-aliasing and aliasing is important. So usually in our hardware, we already give you this anti-aliasing filter there already. So you should not worry about high frequencies will be reflected into low frequency. So don't worry about that. So right now, let's talk about S and Z. So you know that this after you sample all these things, so it's just a kind of like this dots, discrete dots. This is the heavy side. Okay, so this is sampling of unit step function. So let's try to check the Laplace transform of the sampled data. So then it is basically written in this way. Okay, written in this way. K and TS. So it is Z to the minus K and it's U. So this is exactly the U, S, and Z. Okay. So what's going to C? We know that Z is E to the power of STS. So this is our exact relationship between S and Z. Okay. So the Laplace transform of sampled signal and the Z transform of the original signal, if these are the same. Okay, make sense? So the S and the Z, this relationship is highly nonlinear. We cannot do that usually in practice. Okay, so we have approximations of it. Okay, so how to map S and Z? And how to, so we have stability domain and constant damping, constant frequency, and so on and so forth. So we only focus on this second order system to see what's going on. So first of all, stability. So if you have continuous, so on the left hand side is continuous time domain. So our stability domain is from left half plane on this hatched area. Then you mapped this into your unit circle. Okay, unit circle. So this is a very one-to-one simple mapping. Okay, simple mapping. So this is a stability domain. Okay, so that's why in discrete time, if you have a pole outside the unit circle, then it's unstable. So you know that you have a pole to the power of k. Remember, so if the pole is greater than 1, then it will blow up. If the pole is less than 1, it will decay, right? Decay. So that's for discrete case. Constant damping, okay, constant damping. So if you draw a line in here, remember we talked about this is the left half plane, and we talk about I need certain kind of safety margin, so that basically I shift my imaginary axis, okay, towards the left. So check this is as a imaginary axis, okay. So then nothing will get into this area. So that's like safety margin. So safety margin. You don't cross the thick black line. You of course will not cross this line. So it's relatively more stable. Make sense? So this is called margin sigma. So this margin sigma corresponding to actually a concentric circle within the unit circle. Okay. And same thing is true if you have a S-plane, you have a straight line in here. So this is corresponding to a constant omega, okay, for any of the omega. So that is omega t radians of that circle, okay. So same thing, we can study the second order S domain model, and we can map this one into a Z domain. I'm going to go quickly because this is pretty standard mapping. Okay, we don't do the root locus analysis, but here is not root locus. Just to show you that if you have a sector domain in here, okay, so different damping ratio were corresponding to the different spiral. So you have a different spiral. So you have a different type of spiral, okay, within the unit circle. So this is called sector field, okay. We don't use this one very often. So using that constant damping ratio, okay. So the question is how the stability domain will be corresponding to each other, okay. So we have already studied that left half plane versus within the unit circle. Okay, so you have a closed loop pole location inside here. What is your closed loop behavior? Okay, so you can imagine, okay. So this is decaying, okay. This is decaying at a certain speed, okay, certain speed. So we have gone through this already, signal analysis. We can skip this one about decaying, okay, about decaying. So basically you have a pole in here, so you also have a pole in here, okay, you have a pole in here. So if you have a sinusoid, decaying sinusoid, then this corresponding to a second order Z transfer function, okay. There's a correspondence there. So at this point, we are going to talk about zeroth order holder, because in the hardware level, they already have that one. But for the theoretical level, we haven't learned this mechanism. Everything we learn is just like a vertical bar, all these dots, okay, all these dots. In reality, you cannot simply give a system a hit, okay, that's not enough. Probably you have to make those continuous. So basically, if you have a point here, you hold it until next time you see, you hold it until next time you see this one, okay, you just hold it. So hold constant. So this is called a holder, zeroth order holder, okay. It's a device, actually. It's a device. It's a hardware mechanism to make that one happen. So in real world, you say, if you say, oh, what is the overall digital transfer function of this one? So you have a ADC, DAC. So you do a digital control system. So you said, hey, what if I look up table, get a G of S in here? That's enough or not? Unfortunately, it's wrong. Okay, don't do that. So because you have a 0H in here. What's the consequence of having a 0H? You hold the signal, hardware. Then from an analysis point of view, we need to study what is a 0H. So 0H, basically you give me a dot, going through 0H, I give you a holded signal. So basically this is like small gate, right? Small gate. We know that this is a delayed gate and this gate, this is a heavy side and delayed heavy side. You minus this one, you get this gate, okay? Get this gate. So what is the transfer function? Yeah, simple. The first one is 1 over S, second one is delayed, T is one sampling period. So then you will get, this is the continuous time transfer function of 0H, okay? But on the other hand, if you have a sampled data, you minus the previous one. So then according to the Z transform definition, what we have is 1, okay? So in other words, the Z transform of G0H is 1, okay? Isn't this beautiful? I think it's great. It's fun, okay? So here's the point. This is related to your quiz question here. Quiz question here. Let me view bigger. Okay. So you can see that this example is the same. So you have a continuous time signal U here, you sampled, then you hold. After you hold it, it becomes a continuous signal. So you apply to the continuous plant, you sample again. So from here, U to the digital signal, YZ divided by UZ, what is the transfer function? You cannot simply do one of S alone. That's wrong, because you need to combine all these together. And the ZOH here is this transfer function we have seen is a gate transfer function. So then this one is 1 minus Z minus 1. So this is according to definition, okay? So the definition we already learned, the definition here. The definition is, the definition we already learned that, which is Z is E to the power of S T S, okay? So this is already there. So therefore, E to the power of minus TS times S, this is a delay. It is my Z minus 1. So this is also delayed at one step, so it makes sense. So the whole thing is a 1 minus Z minus 1, but you need to combine these two as a system, okay? So you need to do that. You need to do that. So you basically you got the 1 over S, like integrator cascaded to the G of S. That's the correct way to do, okay? If you simply do this to get a GZ, that's wrong, okay? Don't do that because you have a zero edge, you cannot ignore. So the final one you should, correct one you should do is this way. You should do 1 minus Z minus 1. Then you do Z transfer function of this G of S divided by S, okay? Divided by S. So that's the correct way to do it, okay? So let's see the example. This is the example for your quiz. You should put it in your quiz. So this one, okay. So zero H transfer function is this, and then GS. So it will become GS divided by S. GS VDI is this one, right? Is this one. And you have Z minus 1 divided by Z. It's okay. So then what is this one? This one is a PFE, right? You need to apply PFE, partial fraction expansion. Then you get the coefficient in here, okay? You use Cuppy, right? Use Cuppy. So then this one, you know, this is a 1 minus Z minus 1 over 1 minus minus Z. And this one, you know, that is AZ, and A is E to the power of TS, okay? And times this alpha, this lambda. Lambda is 1, okay? So that's how we get in the end, okay? The Z transfer function from, this is Z, okay? The U star means the sample of the data, digital, okay? So this is also digital, okay? So it's from here to here. What is my G of Z, okay? G of Z, okay? So then it's Y of Z divided by U of Z. So then you need to consider zero H. Then you need to extract this term and divide it to GS divided by S. So this you should know. If you don't follow this step, you ignore this zero H, it is wrong, physically wrong, okay? You cannot escape the zero H, okay? All right, so the zero H is basically interesting. So I told you zero H is like this, okay? But in the frequency domain, you put the S is J omega, then you get this one, right? Get this one. So if you check the amplitude, you will get something like this, okay? And this one can be written as a sinc function. This is a sinc function, okay? Remember, sinc function is called S sine X divided by X, okay? If you do sine X divided by X, it's kind of like this, okay? So think about it through a ping pong ball. The ping pong ball will hit the ground and jump and jump and jump and jump. Okay, so this is called sinc function. Okay, so there are some of the derivations. Probably we can ignore that, but it's pretty straightforward to understand that this is magnitude is like this, phase is like this, okay? Phase is like this. So basically we can see it is frequency, the zero order filter. Zeroth order filter is like decaying, like low pass, okay? But you have a pure half step delay. This is like half step delay. It's like the sampling frequency, a sampling time divided by 2, then times omega delay. Okay, this is the delay. Because if you have a e to the power of minus s tau, the tau is delay. Okay, tau is delay. So j omega tau is minus omega tau is the angle. So this tau in our case is this one. Okay, it's a phase lag. So 0h will add a little bit of phase lag there. Okay. Oh, we have seen this already. I've seen this already. It's very interesting. So you have this one, you do a Taylor series expansion and 1 minus, you have this one left over. Okay, you have this one left over. Then you do this again. So then you approximate this to exponential again. This is pure delay, isn't it? Yeah. So this is the sinc function, okay? So again, for block diagram, you have to talk about sampled versus, so this one to this one makes sense, okay? But if you say, oh, I want to check this one and this one, that probably is not making sense, okay? So with 0h, you need this term additionally. Then this sampled data times this is, then you do the sample again, you get a ys, okay? Then y star divided by u star is your z transfer function. So, so this is some argument in the end. So u and y, so you have transfer function, okay, transfer function. Okay. So let me do something here. So you have, let's say you have 2 continuous blocking here. With and without this one, it makes huge difference, okay? So if you have sampling, okay, so you do y star versus u star, so this is okay. So, and then yz is g2 dz, dz is, so if you have samplers between them, you should do this way. But so it's G1Z, G2Z, you can do independent. But if you don't have sampler, so then you have the G1, G2 add together, then you do the Z. So this usually is different. So you multiply together to Z transform. It is not the same as G1Z, G2Z in general, okay? So sometimes and they may not be exist. So for example, you don't have this sampler in here. So what you have is this one, okay? So multiply. So then you do this, then you sample again. So you end up with this one, okay? So you do Z transform of Z1, Z2, G1, G2, then do Z transform. You can do a PFE for that, okay? Which is okay. You can do a lookup table, okay? But if you have a sampler in here, the things will be different. So you simply can do Z transform of this guy, Z transform of this guy, and then you multiply them. Okay. Okay. So, but it's possible that, so if you have sampler in here, sampler in here, so this is just G1 plus G2, okay, which is okay. G1, G2. But if you miss one of them, you cannot even write a transfer function. It does not exist. Okay, it's messed up. Okay, you cannot pull out the UZ anymore. Okay. Anyway, so in general, you should put the sampler in the right place. So everything here, this is a continuous. So here, this is a continuous. And this ZOH is to turn all those dots into continuous. So that's the whole picture. That's the whole picture. This is ZOH. Okay. And you should do this Z transformation of GPS considering this ZOH by doing this star. So having this type of sampling idea will not make you confused. Like, yeah, if you don't have sampling here, you do this way, then it may not have a transfer function. Okay. So we talked about control tasks previously. So there are two types. One is a set point is a constant. So this is called regulator. Like your room temperature, you want to maintain a certain temperature. So that reference is constant, is a regulator. But what if your reference is a curve? Then you need to track on that. So this is tracking controller. Okay. And so I think that this part is pretty straightforward because we put the sampler in the right place. So everything it looks right. Everything looks right, like the transfer function here. So in the end, okay, in discrete time domain, the Z word, okay, I call it S word over Z word. You actually can write something like this block diagram for this set point problem, okay? Again, make sure you do a ZOH. When you get this GZ, you need to keep this one in mind. You simply do original GS and the Z transform. This is wrong, okay? So ZOH is important. Lots of people forget that. See, ZOH is here. So regulator problem. Then you have a disturbance, okay? Disturbance, you can consider that. So then we need to talk about stability. Usually we talk about BIBO stability. You have bounded input, you have bounded output. So what is the condition for stability? It's quite similar to the continuous time. So basically we check the denominator and write a Z polynomial and check whether all the poles are within the unit circle. Okay, so if everything within the unit circle, then we call this is stable. If at the boundary, then it's called critically stable. But if you have a multiplicity more than one on the unit circle, then it is also not stable. Okay, anything outside the unit, it is not stable. So be careful about the multiplicity. Multiplicity when you have a pair of complex conjugate pair on the unit circle. Okay. So how to test whether this is stable or not? Using MATLAB or Simulink is easy, and we don't learn this type of thing anymore. Okay, we usually use brute force. So it was a bad word for using a brute force, but today it's okay to use brute force. Okay, but there is a systematic way to do it. It's called bilinear transformation. So remember, you have polynomial in Z, you get the roots. It's hard to do the roots manually without computer, but I still want to check the stability. Can I use the Routh-Hurwitz test? The answer is yes. You replace the Z in here with this equation. Okay, this is called bilinear transformation. So you turn the Z into W domain. Inside W domain, you get a new polynomial that is all in the W. So then you can apply Routh-Hurwitz, okay? This is kind of tedious when the order is high. But if you don't have a computer with you, so manually, you can still have a way to do the test. Okay. Using a Rousse-Hurwitz table. Do you still remember Rousse table? Yeah, you should do that. You should know that. This is definitely within the knowledge I need to check with you in the final exam, okay? But perhaps not Z. It's too tedious. Not. Just tell you there's a way to do it. So, and stability is not dependent on your external disturbance, okay? It's only related to your polynomials of your characteristic, okay? So stability is assured if original system is stable. So it doesn't matter you have, this L is your disturbance, So this is coming to a very important part. So people may say, oh, I got a solid training in continuous time domain. So you teach me everything in the Z domain on this picture, Z domain, this picture. So do the design. Yes, there is a dedicated book on this Z domain design. We don't have enough time to learn that. I believe we can still leverage everything we learn in continuous time domain. So I say you have two logic steps in here. You turn all the continuous time domain into Z domain, and you live in the Z domain, design in the Z domain, implement in the Z domain, fine, okay? So the second logic is more realistic for us. So you live in S domain, you design in S, then in the end, you get a controller in S, okay? Then you try to make the controller implementable in digital domain, because when you implement it, it's computer controlled. So, but when you do the digital implementation, you somehow can say, oh, they're equivalent. But the question is how you can claim that, okay? How you can claim that. So this is an approach called discrete equivalent design method, okay? So then in the end, it's like, oh, how you can find a discrete equivalent of this DFS? What do we mean equivalent? Equivalent in what sense, okay? So if you have DZ, then you can implement as a filter, okay, digital filter. So the first equivalent is simply say you have same input, okay, and this is a digital. So these two, if they are equivalent, is fine, right? Okay, so can we say the digital version and the original continuous version are equivalent? Okay, so what do we mean? So here is a very quick review. You probably already learned that. Fortunately, if you have any of S transfer function, you want to get a Z equivalently, you have C to D, okay? This command is called C to D, continuous to discrete. So you can imagine there's also D to C, okay? D to C. So when you do the C to D, you see lots of options and you don't understand what are those options mean. So then I'm going to explain to you after the end of today's lecture, you will understand all the ideas in the option. What are the options? The first one is called backward and forward and trapezoidal. You already probably heard about that. Let's check. The other two is called pole zero and mapping and hold equivalence. Okay, let's see. So this is a typical PD controller. Okay, PD controller. So this is a E and K. So this is a proportional control. This is different. This is a derivative control. This derivative control. This is ideal derivative. Okay. So we add a low pass filter. Okay. Add a low pass filter. It's called practical differentiator. This is a practical differentiator. So the practical differentiator plus this one, then you can see, oh, this is a TS. So do you know that this is actually corresponding to what we learned, lead lag controller, right? Lead lag controller. So the reason we add this one from this body plot point of view, if you don't have a low pass filter, the high frequency will get very high amplification, okay? Very high amplification to infinity. So the system without low pass filter, ideal differentiator will make the system very noisy. The very noisy control signal will make your mechanical component warm very quickly. Think about the gearbox, that your gear is doing very high frequency frictions there. You get warm quickly. So you need this one. So if I ask you to draw a block diagram, what is a practical differentiator? You should write this one, okay? And the rule of thumb to choose the N is about 10 to 40, okay? So with N is bigger, N is infinity, then it's zero, right? It's ideal. So the bigger the N, the large the frequency band. So depending on your practical frequency range of interest. Okay, so we look at the derivative term. So this one can be written as a difference equation. Then we can write in terms of realization using op-amp, remember? So you can write a integration and then do this feedback, right? This feedback. So usually this is a negative feedback. So let's do this. Say this is N TD, this integrator is 1 of S. So then this is a feedback, so it's 1 plus N divided by TD, 1 of S, okay? So you can see I cancel all S, I have S in here, right? S in here. So this is exactly what we have, low pass filter, okay? So this is a low pass filter, okay? So how we can implement this integrator, I already told you, this is a shaded area, this is trapezoidal, okay? Trapezoidal. So we can use forward rectangle, we can use backward rectangle and trapezoidal. So then basically 1 of S is like this one. Or 1 of S is like this one. Another idea is like this, okay? Is this sounds familiar? So this is also called Tustin transform, okay? Trapezoidal or Tustin. So remember, this is 1 of S. Then you reverse that. Your S will your S will be like that. So then you also can write what is Z in terms of S. Okay, Z written in terms of S. Okay. So I think we have equation here. Yeah, Z in terms of S. So S in terms of Z, Z in terms of S. So currently we try to get S discretized. It's called discretized. But it's also possible you have Z, then you want to get S. Okay. So can we also write this one to S? Yeah, we can. So this is so this should just do this one. So then we have a T plus T Z minus 1. You have S, you also have S. Then here I have 2 minus 2Z minus 1. So then what I need is to collect the Z's. So I put this one inside here, this one inside here. I have 2 minus ST. All right. Yes. 2 minus, wait a minute. 2 minus st. And this side is ts plus 2. Okay. Ts plus 2. And you have z minus 1. So this one is this side. Okay. So you move this term this side. Okay. And keep the 2. 2 minus st is this side. So 2 minus st divided by 2 plus st. Is that right? Okay. Okay. So I can write this one as a 1 minus st divided by this. 1 plus st 2. So this is z. This is z. Actually, this is z minus 1. This is 1 over z. So you can replace it. So you will become like 1 plus w, 1 minus w. So let me go back to check whether this is correct here when we see the stability. I think we passed it. Do you see that? Here we have 1 plus w, 1 minus w. Okay? Why? Why? Okay. This y answers here. Okay. W is s times t divided by 2. So so in z, it's hard to do. You can do in w by this. It's like in the S domain. So probably we should visualize the stability. So this is a complete PID controller is in this form. So this will add you to the so this is, remember, is a PD with practical derivative, then it becomes a lead lag. So we can write this one in terms of difference equation. Then we implement this one in the difference equation. Okay. So easy way to do is to replace s to 1 minus z minus 1 divided by t. So this is a, so then you will get something like this. You get a gz. Okay. So this is called cs. This is called cz. Okay. Cz. Then this cz will get you a difference equation. You can implement it. But what if I put a different here? So it could be this one, could be this one, could be this one. Okay. I already told you the W-plane method for the stability. I'll talk back this one later. So I already derived this equation for you. But remember, these are all approximate relationship of this. This is a 100% true relationship. Okay. So what's the definition? Well, why we do that? So for S domain, I have a left half plane. So then if I do this linear relationship like I did in here, okay, like in here, then the Z domain, it is an exaggeration of my unit circle. It's supposed to be here, but you did more than that in the strip in the Z plane. That's not right. Okay, something wrong. So it's dangerous sometimes. Okay, if you use backwards, then you end up like this one. So which is this one. Okay, then you'll see that it is conservative. Okay, so but on the other hand, this one is giving you 1 equals z minus tzs. Okay. Then I write s to Z. S equals 1 minus Z. Sorry. It's Z minus 1, this one, this side. So this is a T times Z. This will be 1 over T, 1 minus Z minus 1. Did I tell you I love Z minus 1 better? It's causal. Okay, it's causal. So by doing that, you only get this. So it's conservative. Conservative. So, however, good news is if you use Rousse-Hurwitz method and you use this equation mapping, they are the same. So that's why Tustin is beautiful. You should try to use it as much as you can. Okay. All right. So this is no conservative, no conservation at all. Trapezoidal. So you can see that now you get S to Z or Z to S. And again, maybe 30 years ago, this is still a topic of research. What's the best way to do? Can we do better than the Tustin? Okay, this is a very good question. So again, let's try to here to use a trapezoid. Okay, so when this is a trapezoid, I'll replace S with this complicated form. This is my S. This is another S. So I put everything in here. Okay, then I put S, Z in the frequency domain is E, J, omega T, S, okay? Omega T, S. Z minus 1 is minus here, okay? So this is Z minus, okay, sorry, Z minus. So you put everything in here, okay? So you can see that if I put omega is 0, okay, omega is 0. So this I'm going to get it. I'm going to get what? I'm going to get a DC gain. You can see the DC gain is still 1. So when S is 0, then my DC gain is K. Okay. So using trapezoid, you are not going to get distorted at the DC frequency, which is beautiful. Okay. But on so at DC, no distortion. Okay. Which is great. Which is great. So on the other hand, if you assuming fast sampling, omega t is small. Okay, omega t is small. So it will become so frequency dependent. So if you have a higher frequency, the distortion will be bigger and bigger. Okay, will be bigger and bigger. So in other words, what's the difference between CS and CZ? Yeah, there's no difference when omega is 0, no difference. But as omega goes up, the difference will be bigger, okay? Will be bigger. So that's actually the problem, okay? So you should seek some other, even if you use Tustin, okay? Even if you use Tustin. Okay. So some people say, oh, I should do some pre-warping. I have some special requirement when the frequency is high, or at certain frequency, I want this one, there's no difference. So yes, there are many discussions about what they call the frequency pre-warping method. So that discrete equivalent can match those continuous time frequency at a DC and matches for low frequency and other frequencies, okay? So by doing that, it is called frequency pre-warping when you do CS to CZ conversion, okay? So you can add those requirements into it, okay? Good. So zero pole mapping, and today there isn't any new research going up, but previously this is good topic of research. Okay, but on the other hand, people may use another idea. It's called pole zero mapping. So this is another technique, pole zero mapping. So basically, they said, oh, I don't know, this to the CZ, yeah, at the omega is 0, you have good mapping, a good matching. When omega goes, the difference is big. Let's probably don't use this S to Z, this one. It's hard. But what if I ensure that for all the poles and the zeros, I use this correspondence? Okay, let's see an example. So again, you have this is called lead lag compensator. Okay, we talk about this. Okay, lead lag, but it also has another name. It's called a Pid Controller with practical differentiator. We're talking about this. Okay, so we have 1, 0 with 1 over t. We have also one pole is here. So then we use this exact relationship. So we can compute what is my 0 in my Z domain. So Z domain. After that, I simply write Z in here. So this is my 0, this is my pole. That makes sense, isn't it? On the other hand, I want also my DC gain to be the same. So I cannot use the K, I use K prime. What is my K prime? Such that my DC gain is the same. So the original DC gain is S is 0, right? But if you have Z transfer function here, how you can get a GC gain? You get a G1. You put Z is 1. Why Z is 1 will give you this one? Because Z is ST, okay? And S is 0 is for DC gain. So then it's E to the power of 0 is 1. Okay. When do this way. When you write S is J omega, omega is 0, okay? Okay. So Z is 1. So if you are giving a GZ, I give you a GZ expression. So then I ask you, hey, what is the DC gain of the GZ? What you should do? Put Z is 1. Okay. So then put Z is 1 is 1 minus 1 minus, and then you can see this equation. You know the K, you know the T, you know T1, T2, then you can solve the K prime. So you put the K prime in here, you guarantee that the DC gain didn't change, right? Isn't this another beautiful idea for turning your controller CS? This is your controller, right? Controller input is E, output is U. Okay, so how to convert this on to CZ. So you have a CZ, then you can implement the CZ as a difference equation, which is a digital filter, IIR filter, which is simple. So that's called a pole and zero mapping. There's another idea, right? So there's also another idea, it's called ZOH equivalent. Okay, I really hope we can do the discretization with the ZOH in mind. So because you have C of Z, okay, so this is still a digital signal. Before this one is also a digital signal, okay. This is CZ, so this is your EZ, and this is your UZ. But UZ should have put something called ZOH in here. So you have continuous signal, continuous time signal. Then you put your plant, okay. Of course, you can do feedback or whatever. You just sample this one, but now you don't because these are analog. Okay, these are analog. So this is analog. So this is digital, okay? So you have a sampler there. Okay, so this is my PD controller with a practical differentiator. Then you have H of S in here. So what he said that, oh, what if I put this one into consideration? So that's why we have this one. You can already see it, right? So this is 0H, okay? So I think our time is good. And we finished all the digital control study, about 140 slides. And I'm going to walk you through here regarding our assignments, okay? As you can see, this is our last homework, as I promised, okay? No more work, just homework. And this homework is more flexible. If you go to sensor, so basically what you need to do is write about 25 slides for sensor and 25 slides for actuator. So then together you have about 50 slides, okay? But we have 60 students in the class. So computing 60 times 50 is 3,000. So we're going to have 3,000 slides. So make sure you name your slides nicely, like this name, okay? So that we download and arrange and we can share back to you. So when you do, in fact, when you do 25 slides, then it's amplified by 60. So I call this a collaborative learning experience, collaborative learning excitement. Okay, I hope you enjoy that. And I'm going to use this one called where is my discussion? Yeah, it's here. Discussion. So you can have look for, okay. So I add a discussion here. So you guys can reply and like assignment number 9, sensors, actuators, choice. So no collaboration, everybody do yourself. My actuator is this, my sensor is, yeah, you can write something like that. So so right now, in my mind, I need to study some actuators like crop duster. Then crop duster is actuated. We actuate some pesticides. Then try to keep those pests under control. My sensor is like a thermal camera. Okay. So I want to do a low cost. I don't want to use commercial, it's too much. So thermal camera, I look at the crops to see whether the crops are growing happily or not. So so this is a call for precision agriculture research. Put on the drone can see them. Or you just put on your hand, you can have a robot to take pictures of trees. The trees under different stress of order or of pest. The tree leaves will respond differently, and then hopefully we can detect that. So okay, so then I save and publish. So you guys can do discussion is so you can subscribe and you can reply. So, okay, so put your name as my choice is what. So then others will not duplicate it. So it's not very interesting to have 10 people doing a temperature sensor. One is enough, right? So with that, 1 minute over time. So enjoy this. I gave you the template already. You just filled up the things. And I think I already have about 10,000 slides collected. So, but don't copy those when I showed you. You do yourself, okay? Like emotion detection, to check your dog is happy or not, okay? Sensor, like that. Okay, so stop sharing, and our next lecture for Friday is on sensors and actuators. We're going to spend 2 lectures on the sensors, 2 lectures on the actuators, and the last lecture is 30th, last day of April. I'm going to, yes, give you more time to do surfing on the internet. Yes, so don't worry. Okay. But you must submit. If you submit, it's non-zero. If you don't submit, it's definitely 0. Okay. With that, I'm going to stop and say goodbye to you. All right. Have a good day, and see you Friday. We probably will not have the lab session even tonight. If you need, you can email the TA, say, oh, can I have a meeting with you? Or you can accumulate your information and to talk to us 1:30 of Friday, our office hour. How about that? So then you guys focus on your lab design, final project, okay? All right, bye-bye then.